In this video, I am going to talk about the kinematics model and the meaning of each of the variables in the equations. It's a little bit different than the average quantities we've been dealing with such as average velocities and average accelerations, which are, like the word implies, the averages over certain intervals. We're going to talk about exact velocities, exact displacements at the end of a certain interval. So it's slightly different. Just as your average grade is a collection of all your grades during the semester, it doesn't pinpoint any one grade. The kinematics model actually pinpoints one of those grades or one of those velocities. So in this example, I'm going to use an example of a car that accelerates. So I'll draw the car here at the beginning and at the end of some interval. When I analyze motion of an object, I'm going to define a couple things here. Where it starts, and I call that x0, and where it ends, x. The reason x is because, as in math class, this is called the x-axis. So this 0 for the x0 means that time equals 0 when I start the stopwatch, because I'm going to time this. At the same instant, I can talk about an initial velocity and I can talk about a final velocity. What velocity does it begin with? What velocity does it end with? And then during this interval, I can talk about an acceleration rate and a time. So there are three kinematics equations, and I'm going to talk about each of those three right now. The first looks like this. The first kinematic equation is x equals x0 plus v0 t plus 1/2 at squared. And what this says is the following. If I know where I start, x0, which 99% of the time is 0 because that's where I start measuring things. If I know where I'm at initially and I am initially going some velocity, v0, so if I'm already moving, this can also take care of the case when I'm actually starting from rest, in which case it'd be 0, like I'm at a stoplight. If I start at some location and initially traveling some velocity and I accelerate for some amount of time, it would seem logical that I could find out how far it traveled, which is here on the diagram. If I know where I start, what my initial velocity is, which may be 0, and my acceleration rate for that time frame, and the time that I'm accelerating, I can find out x. Unit-wise, and I'm going to use the SI metric system, x is in meters, x0 is in meters, because it's a displacement. Velocity is in meters per second. Time is in seconds. Any number, like 1/2, has no units. It's a unitless number. Acceleration is meters per second squared. And time is time squared, so it's second squared. So if I look at this with units, a meter equals a meter plus a meter plus a meter. So this equation is dimensionally correct. The moral of the story is this. Make sure every quantity, like x's and velocities and accelerations and so forth, are on the correct units. If I do so, then I can be assured the final answer comes out in the correct units. The second equation is v is equal to v0 plus at, which says the following. If I'm starting out at some velocity, right here, and I accelerate for some amount of time, t, I should be able to figure out what my final velocity is. And this is what it says. Starting at v0, again, this may be 0 if I'm starting from rest, like a stoplight. If I accelerate for some amount of time, I should be able to figure out my final velocity at the end right over here. In terms of units, this is meters per second equals velocity meters per second plus acceleration is meters per second squared, and this is seconds for time. So a meter per second equals a meter per second plus, and if I cancel one of these guys out, a meter per second. So again, the moral of the story is, if I make sure that the units that I put in are consistent, I can be assured that the units of the final answer are correct. And finally, the third equation is v squared is equal to v0 squared plus 2a x minus x0. Again, you will not have to memorize these as you're on the equation sheet. You're going to have to know how to use them, which you'll see in later videos. So what this says is the following, and for right now you can ignore the squares, it's just a mathematical thing. If I start out at some initial velocity, right over here, and I accelerate over a certain distance, now notice that there's no time here, it's over a certain distance. So I accelerate over 100 meters through an intersection, or so forth. If I accelerate for some distance, I should be able to figure out my final velocity. So this is independent of time. Unit-wise, again, this is meters per second, but it's squared. So it's meters squared per second squared equals meters per second squared plus the number 2 is just a number, it has no unit. Acceleration is meters per second squared. And this is, right here, a meter minus a meter. So a meter minus a meter is still a meter. So I'll call that just a plain old meter. So if I look at the units here, meter squared per second squared equals meter squared per second squared plus meter squared per second squared. Again, making sure that if we have all the units correct from the beginning, that we'll have the correct units at the end. So these are the three kinematic equations we can use to solve for values at specific instants of time. Again, this is unlike average quantities like average velocity, which is just a change in position over the change in time, or average acceleration, which is the change in velocity over change in time. And again, the best example I can give is in terms of your grades. An average grade is representative of all your grades, but does not pinpoint any one particular grade. That's what average is. These kinematic equations pinpoint an exact velocity, an exact displacement, an exact time for a specific interval. So it's a little more exact than the average quantities. Nevertheless, you have at your on your equation sheet average equations and your kinematic equations. In later videos, we are going to talk about the procedure that you use to solve problems using the kinematics model with these three equations.